All right. Happy Monday. Here we go. Before we start, I did post this today. I posted a Hello World assignment from last day, right? Gave you the weekend off, figured you'd had enough on your plates. And so that is due next Monday. So I try to give you a lot of time to work on things. But if you're like me, then you end up putting it off until probably Sunday night. That's okay. It happens. That's just how it goes. Everything else comes up. Quicker due dates. Oh, start of the term. You're probably thinking, oh yeah, I'm going to be so on top of things. And maybe you are. Maybe you're a better student than I am. Maybe a better person. You'll notice what happens here so I posted a little, it is an RMD document, but Moodle can't seem to handle it. I don't know how to change that. And so that's okay. What happens is when you click on the assignment, and I think you'll find that it's relatively easy. When you click on the assignment, it takes me to just this text file. So what you can do is you can just copy all of that and paste it into a new Markdown document, right? So clear everything out, paste this in, and then, or if you just want to start a fresh one and use these questions, that's fine too. So kind of basic things, right? Show me that you know how to work in Markdown. So write your name in bold, italicized, and then both bold and italicized, right? We practice that. And then headers, and then make a bullet list, make a numbered list, change it up, see what happens. The only thing that one of the things that we didn't talk about on Friday that I'm kind of nudging you out of the nest, I guess, is I want you to make a table in Markdown. So of course that involves Googling, how do I make a table in Markdown? And that'll be really useful. And I have some criteria. I want 3 columns, 1, 2, 3, right? And 4 rows, 1, 2, 3, 4, and a header row. So technically there's 5 rows. And you can add information into the table if you want to, or just kind of space holders if you want to, right? I'll leave that up to you, get creative. And then I'm getting you to make an R code chunk. I don't think we got to actually doing calculations in R. So this might also require some Googling, right? And that's okay. You can do it. You can handle it. Notice that it's got, so I'm trying to see here what I can do. Save. Oh my gosh. My allergies just decided that today was the day to really act up. So when I tilt my head forwards, my nose just starts dripping. I don't know what to do there, but it's really gross, and I'm glad we're not in person because that'd be nasty. So here I am just kind of handling my own scandal, I guess, or not handling my own scandal. Wait. So the Hello World assignment is due Monday, September 27th at 11:59. So a lot of these are easy, right? But this one is kind of a little bit harder, right? Insert a table, but I'm confident you know or you will find how to do it. Okay. The reason I brought this in is because I wanted to highlight this here. So this is an example of how you would write a mathematical formula in Markdown. Okay, so when it's surrounded in dollar signs like this, that's LaTeX code. Okay, so LaTeX is just, it's going to make it easier to write these kind of Greek letters and anything that is going to be hard to type, like Greek letters, math functions, that kind of thing. Okay, so that's when we use LaTeX. What you'll see, and what I want you to do, is I want you to copy this whole chunk, right, all this text into a new Markdown document, right? When you knit it, right, you can just knit it. It should just knit on its own, or once you press knit, you'll see how this generates. Okay. I didn't want to give it to you because I want you to knit it and see for yourself, right? But it should end up looking like 4 minus 3, oops, 4 minus 3 divided by 1.2 divided by the square root of 45. Okay. So this is called LaTeX code. And it's kind of like this capital L, lowercase a, capital T, lowercase e, capital X, LaTeX. Okay. And so I just wanted to introduce it to you like this. You don't have to include it or anything, but it's worthwhile playing around with. Okay. And eventually what you'll find is that you'll want to show something that looks a little bit nicer, and eventually you'll end up using LaTeX code just kind of by, I don't know, you're out of options for anything else. So eventually you will want to use it. And here's your first little taste. Okay. And then I wanted to end it. I want you to add a comment, right, to your R code saying the end. And then knit it, make sure it looks the way you want it to, right? Producing the tables and they look the way you expect them to, and then submit that HTML file on Moodle. So if you have any questions about that, let me know. But chat's pretty quiet. It's Monday afternoon. No one wants to chime in. Say, hey, that was rude. We could have been working on this all weekend. I know. I wanted you to have the weekend off. Next weekend, you can work on it. All right. So, and if you have any troubles come up as you're working on this, then obviously let me know. All right. Hey, look at all these cameras on today. So fun. I'll be all distracted. See what's going on over on your guys' end. So that is good. So we talked about, in terms of review, right? We talked about measures of center. We ended on measures of center. And so I'll just bring them up here. Measures of center, which included the mean, right, which is the average, the median, which was the central value, and then we talked about the mode, and we finished talking about the geometric mean. Oops. Geometric mean. How about that? Okay. Oh, hey, fancy hand. Yeah.
Hello.
Hey.
I'm just trying to download this Hello World assignment. It's supposed to be an RMD file. Is that correct?
Moodle makes it a text file. So what you'll have to do is you'll have to open it so that it looks like this. When you click it, it should open like this, right?
Yep, it does.
So then what you'll do is you'll copy all of this into a fresh RMD file. So when you open up a new RMD, you'll clear it so that it's completely empty and then just replace it with this. If that makes
Okay,
sense.
open a new R Markdown
Yep.
or R script.
No, I'll share my other screen here. Let's see here. How do I get back here? Got it. Stop this share. Start this share. Okay. So what you're gonna do, is it sharing my screen?
I can see your screen.
Cool.
I'm looking at through Moodle.
Let's see here. So it should open like that.
Yep.
And then what I would do, just so that I kind of have the questions and kind of plug away at them, I'm going to copy. So I just highlight it all or control all, copy, and then paste it. My RStudio isn't on. I need a faster computer. Now I have a reason to.
You don't have all day, Emily. Jeez.
I know, right? So then what I would do is I would say, open a new R Markdown file here. And I'm just going to click OK because I'm not going to keep anything. And then here, I would just empty it and replace it with that one that was there.
Okay. And then you just save it and knit it that way and it's all good to go.
Yeah. Yeah. So it should knit and you should see, oh, well, I haven't saved it. So I'm just getting caught up on the chat. Thank you. Nice. So I think from there, yeah, once you save it, you'll be able to knit it and then you'll be good to go.
Okay.
And you don't have to keep this list in your submission. You can just kind of answer those as you go. So I'm going to stop this share, start the other share again. Okay. Hey, that whistle sounded kind of creepy of me. Sorry. Here we go. Okay, so here we go. So hopefully that makes sense, but if it's giving you grief still, then let me know. All right. So we talked about measures of center, and really what we should be doing is we should be calculating these using software, right? So in class here, we just talked about what they were, right? How do we calculate the average, right? So the mean is the average, right? The median is the central value. Oops. The central value, assuming that you've sorted your data from smallest to largest, right? Then that's the median. And depending on how many data points you have, right, there are a couple of different rules, but in general, Excel, if you prefer to use Excel, that's fine. for doing these quick calculations. Excel will just do it for you, or R will just do it for you, right? And then the mode is the most frequently occurring value. Occurring value. And then the geometric mean is kind of this fancy mean, and we use it when we have dependent observations, right? So things like stock prices by day, right? They kind of depend on the previous day. And same thing with weather, so temperatures, that kind of thing. So as soon as we have some sort of dependence, then we should be using the geometric mean, which is really just, I shouldn't say just, we multiply all our points, whereas before when we were calculating the average, we added them all up, right, and divided by however many there were, right? Whereas the geometric mean, we multiply all the points and then we take the nth root, right? So here, the mean, the sample mean is denoted by x bar, which is the sum of the x's over n. Okay. Whereas the geometric mean, we denote by a little subscript g, because that's unusual, right? Typically, if we're talking about the mean, we're talking about this mean here, the arithmetic mean, but the geometric mean is going to be, we didn't talk about product notation. So how do I write it? Well, I'm just going to do it. The product of the x's and tell you the product of the x's, all data points. And then to the power of 1 over n, right, where n is the number of data points, which is the nth root. Okay. But again, software is just going to do that calculation for you, right? But it's good to have an idea of where it came from. Okay, so that's kind of all we need to do for review for today, because now we want to talk about measures of variance or variability. Okay, so still in the chapter 2 notes, we're going to talk about measures of variability. Hey, delete. There. So for example, if we're talking about maybe this data set here, or these two data sets, just to get an idea of what's going on here, I'll just zoom in like this. We have two funds, Fund A and Fund B. Okay. Now, if I asked you just intuitively, right, which one has more variability, right? I think that you would choose Fund B, right? There's more variation here. There's more fluctuation as you move from year to year, right? Whereas if you kind of scroll down through Fund A, you're actually seeing no variation, right? And so here we're seeing, so Fund A, we notice that Fund A has no variability, right? Whereas Fund B has, quite a bit of variability, especially compared to Fund A. Okay, and so that's what makes Fund A a safer choice, right? Fund B is maybe more more fun to invest in if you like having ulcers, it's down, it's up again, but less. It's still up, but you wanted it up higher, right? And so you've got this kind of roller coaster ride, right? Notice also that they have the same mean. So you can have the same mean, the same average, and this is the arithmetic average because otherwise they would have to say the geometric mean. And so they're centered on the same values, right? So the only difference here is the variability. Okay. Centered on the same values. Okay. So what are some measures of variability, right? That's what we're here for. So we want to be able to quantify that variability, right? That kind of roller coaster action. First thing we're going to talk about is the range, which is definitely the simplest measure of variability. Okay. The range in this case, which might be a little bit different if you're, depending on where you're coming from in math, but the range in this case is going to be the maximum minus the minimum. Okay. So the range in our case is going to be the maximum minus the minimum. Okay. That's easy enough, right? That gives us some idea of the variability, right? Especially here, fund A would have a range of 0, right? Because 1100 is the maximum, but it's also the minimum. So when I subtract those two, I get 0, right? So there's 0 range, which is a measure of variability. Whereas here, I haven't looked at these too closely, but I'm seeing a 300, a 100. Oh, yikes. That was a bad year. And then the max looks like it's 2,500. So here I have a range of 2,400, right? Quite a large range. So now that's one measure, and I didn't look at it too closely, but I think I got them. Who knows? Right, but that's one measure of variability. We have fancier measures. You might have heard about the variance. Have you heard about the variance? So the variance essentially measures the distance between each data point and the mean, right? How far away is each data point from the mean of that data? Okay. So the variance is the deviation about the mean. And so how that ends up working is we take each data point, subtract the mean, square it, right? So if you're doing these by hand, you would probably be making multiple columns, right? You'd have your column of your actual data, and then you'd have a new column of each data point with the mean subtracted. And then I like to make another column of data where I square each of those values so that I can eventually add them up, right? That's a lot of work. We're not doing that. We're going to make software do it. Got this fly in here, and it just will not, it can be anywhere in the house, but it just wants to be here. So that's okay, I guess. So that's the sum, right? And that's a big calculation, especially if you're doing it by hand. Imagine you've got 20 data points, yikes, right? Whereas R or Excel can easily do this calculation. Notice that we're dividing by n-1, right? And so the difference here, and the only reason that I have these little side notes where we talk about the difference between the sample variance versus the population variance, so I'm going to bring this in here, is because for the population variance, we only divide by n, the population size. Okay. So notice for the population, for the population variance, we divide by n, right? Versus here, right? For the sample variance, we divide by n minus 1. The explanation for that is pretty tricky. So I tried to hunt down, they were calling it a more intuitive explanation for why, but just briefly, if you're curious, or if you're not, you can tune me out for a minute. So the reason is because the sample variance is closer to the sample mean than it is the population mean. And so, hey, thanks. So then when we divide by n minus 1, we make it a little bit larger. And so then it becomes closer-ish to the population mean, which is what we're trying to do. But that's all kind of weird, and there's proofs and stuff, but we're not doing that. For you guys, what I want you to remember is that most of the time we will be dealing with sample data, right? And so you're going to be dividing by n minus 1, or your software is going to divide by n minus 1, versus if at some point, and usually we like to be a little bit sneaky and have, a multiple choice question saying, say the population is this, blah, 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 find the variance, then you would divide by n, not n minus 1. That's sneaky. I don't want to do that. But it does happen, and it probably is going to come up in maybe other courses. So just keep an eye out for that. Okay. So let's see here. So that's just something to remember. And especially if you're working with Excel, it'll ask you to specify, do you want the sample variance or do you want the population variance? And so that's the reason, is because the calculations are different. One other tricky thing about the variance, notice that it's s squared. Okay. The tricky part is that the units for the variance are squared, which makes them really hard to interpret. So if X is in dollars, for example, then the variance is going to be in dollars squared. And that's hard for us to think about. And so that's why we tend to use the standard deviation instead. Let me write that down though, before I introduce the standard deviation. So the units for variance are squared, right? The units of X squared, okay, which makes them hard to interpret. Or maybe not. Maybe you feel comfortable talking about squared units, but I don't. I think that they're hard, right? Which makes them hard to interpret. Which is why we typically, prefer the standard deviation. So let me bring in the standard deviation here. the standard deviation is the positive square root of the variance, right? And so that's how we're going to get rid of that square. And so notice that it's really just the variance square rooted. Right? And it's the sample variance. And so the standard deviation is just the square root of the variance, the positive square root of the variance, mostly because we can't have a negative spread, right? We're always going to have either zero spread. You can't have like a negative spread. It doesn't make sense. So it's going to be positive. But most people just, when they take the square root, forget that you get a plus minus. So usually it's pretty safe. Okay. So the standard deviation requires that we find the variance first, typically, especially if we're doing it by hand or not. So usually you can just go straight to R and it'll calculate the standard deviation really easily for you. But it's quite an involved calculation if you're doing it by hand, right? You'd have to follow all those steps for the variance and then take the square root. People always forget to take the square root. Okay? But for us, right, it's just a measure of spread. And again, it just goes back to the variance around the mean. So how far are values from the mean, each value? The textbook also introduces the coefficient of variation. I just have a little warning about the coefficient of variation. The coefficient of variation is used in economics and it is used in actuarial science. Have you guys heard of actuarial science? Yeah, cool. So basically kind of dumbed down risk assessment, basically. And so they use it a lot. But there are cases where we can't use the coefficient of variation. But all it is it takes the standard deviation and divides it by the mean, basically asking, or the calculation is telling you how large is the standard deviation compared to the mean, right? And so typically, if you have a coefficient of variation less than 1, typically, and it kind of depends on the field that you're in, so I'm being vague on purpose here, but typically less than 1 means that you have low variation, right? So low variability. So a CV, coefficient of variation, right? CV, less than 1 usually indicates low variability. Right? And then as it increases, it's just a measure of how variable your data is. So one thing that I do want to note is that the coefficient of variation can only be applied to data that has a true 0. So what we mean by that is 0 has to mean 0 things. There's nothing there. Okay, so $0 means that you have no money, right? Whereas 0 degrees Celsius doesn't mean that there's no temperature. It's just another temperature, right? And that's where we cross from positives to negatives. But so that's the difference. And so that's just a warning for the coefficient of variation, but especially in terms of money, it's going to work. So, and it's pretty common to use. So just a warning about the CV. It should only be applied to data with a true zero. Oh, doesn't look like with a true zero, right? So for example, $0 is no money, right? Whereas temperature has no true zero, since 0 degrees Celsius is not a lack of temperature, right? It's just another temperature. Okay. So it's just a warning, something to keep in mind, or at least so that when you go to calculate, yeah, exactly, measurement versus a quantity, if you want to think about it that way. But my goal here is not to have you memorize this, but rather, if you find yourself calculating the coefficient of variation, I want a little trigger in your mind saying, she said something about be careful. And then you can go and look it up, right? So I just want you to have like a little bit of a stop here and say, okay, well, we can calculate it for any data, right? Because we can find the mean and the standard deviation of any data, right? But the actual interpretation of the coefficient of variation only applies if you have a true zero. I'll leave it at that. Okay, good. So we're calling it analyzing distributions. I wouldn't call it analyzing quite yet, but we are digging a little bit deeper. So what are some of the characteristics of our distributions? So what are some of the characteristics of our data? So a common measure that we have is percentiles, and you might have heard about percentiles with grades, for example, or you know, your stock portfolio is in the top 10 percentile or the 90th percentile or whatever, right? And so percentiles, we use them often, and finding them by hand, again, really tedious, really hard. So we're grateful for software, right? But in terms of what they are, is that the pth percentile, so usually we use p for percentile, so the 90th percentile would be the point that separates the lowest 90% of your data from the top 10%, right? So there's a point there, right? So for example, the 90th percentile separates the lowest 90% from the highest 10%. So the percentile always has that percentage below it. Okay? We've already talked about a percentile, but we didn't call it that, right? The median is a percentile. It's which percentile? It's the 50th percentile, right? Because it splits our data in half, right? It's the data point that splits our data in half. So we have the lowest 50% below it and the highest 50% above it. So there are common percentiles that we use, but in general, we use software to find them, right? And the reason for that is because the only nudge that we have in terms of a formula is only finding the location of the pth percentile, right? So it takes the number of data points that you have, it adds one because otherwise it might get thrown off. we can play it out, but we're not actually going to do it by hand, so I'm not going to do that. And then we have to multiply it by P, which is our percentile over 100. So if we want the 90th percentile, we would do 90 divided by 100.9 times however many data points, right? So moving 0.9 through however many data points we have. So here, notice this only finds the location, not the value. Use software to find the actual value. Use software to find the value. Okay. So there are kind of set percentiles that we talk about often, and those are the quartiles, which splits our data into quarters. And we already saw it in that summary output, right, where we had in that default RMD file, right, when you knitted it to HTML to practice, it produced a 5-number summary as well as the mean, right? And so the 5-number summary is the minimum, the first quartile, the median, the third quartile, and the maximum, and then it throws in the mean just for good measure. So let's talk about the quartiles. I put them over to the side because they're kind of a subgroup of the percentiles. And I probably wanted to keep things on one page or something like that. Who knows how this mind works. So our quartiles are exactly what you think they are. They split the data into quarters. And so usually we use a capital Q subscript 1 for the first quartile. So that's going to be your lowest 25% of your data. So of course you've sorted your data from smallest to largest. And then your second quartile we've already talked about is the median, right? Because it splits your data in half, or 2 quarters, 2 quarters. And then the third quartile is the 75th percentile because it's got 75% of the data below it and then 25% of the data above it. So we often talk about the interquartile range. Inter means between, right? Between quartile. Range is the distance between Q3 and Q1. So the interquartile range we usually abbreviate as IQR, and it's going to be Q3 minus Q1. Oh, scared me. Door opened. It's okay. So here, this is referring to an example that we're not really following, right? But once we have our quartiles, which you saw in that summary output from R, it's easy to find. Then you can find the interquartile range. So what's nice about the interquartile range is that if you have really extreme values in your data, right, then the interquartile range can still give you a reasonable measure of spread without including those, right? It just looks at, if we think about the distance between Q1 and Q3, right, then it just looks at those middle 50% of your data, right? And so it basically lobs off all these extreme values on either end if you have them, right? And so here, it excludes some of those extreme values, or if your data is really skewed, then a more reliable measure of of spread is going to be the interquartile range, right? So the interquartile range is a more robust measure of spread than, then the standard deviation for skewed data. Yeah. So if we have skewed data, then we should be using, or we should be looking at the interquartile range for some measure of spread. Good. So another fun thing that we use quite a bit, oh, I didn't copy it right here, are Z-scores. So Z-scores, you may have heard about Z-scores before. They're going to be standardized values. So Z-scores take into account where is the center, but also how much spread is there, right? If there's a lot of spread, then a distance of 10 from the mean, if we have a spread of 30, a distance of 10 is not that big of a deal, right? But if we have a distance of 10 and our spread is only 2, then all of a sudden a distance of 10 is really, really large. Right, so we need some way to communicate that, and the best way to do that, or the easiest way to do that, is with Z-scores, right, or standardized values. So let's see here. A Z-score tells us how far an observation is from the mean, taking into account the spread, right? And so how we find it is we take, so ZI means that we can calculate a Z for each data point, right? So each data point is going to have its own Z-score, its own standardized value. So you take each data point, subtract the mean, and then divide by S, right? How far is that observation from the mean when I take into account the spread? Okay. And so this says that each data point will have its own standardized value. If a value of X is below the mean, how's that reflected in our Z-score? If X is less than X bar, right, then just, so what I like to do when I'm faced with these problems is I like to just take example numbers, right? 3 is less than 4, right? So then it's easier to work with 3 and 4, right? 3 minus 4, okay, I get a negative number, right? And so, and the standard deviation just can't be negative, right? It's always going to be positive. So if the observation is less than the mean, the Z-score is going to be less than 0, right? It's going to be negative. So if an observation, right, which is X subscript I, is less than the mean, X bar, we know Zi will be negative. Will be negative since S, or I should say the standard deviation first, since the standard deviation can't be negative, right? If it could be negative, Well, that makes a mess, right? Because then you could have a negative divided by a negative, which makes a positive. Uh-oh. Right? But luckily we don't have that. We don't have to deal with that. So if the numerator is negative, then overall the thing is negative, right? Whereas if xi is above the mean, right? Now imagine a value larger than our pretend x bar. I think I made it 4 or something like that. How about we do 6, right? 6 minus 4 makes a positive number. So now I'm getting a positive value, right? So negative values mean that the observation is less than the mean. Positive values mean that they're above the mean. And then the actual magnitude of the z, right, tells us how many standard deviations away it is, right? Let me write that down. I guess I should end it with an observation above the mean will yield a positive Zi. Okay. The magnitude, or what I'll say is I'll say the value of Zi tells us how many standard deviations, one more. How many standard deviations, are you guys okay with just SDs at this point? Good. My hand. Couldn't possibly write out 2 words. The value of Zi tells us how many standard deviations above or below the mean an observation is. An observation xi is. Kind of a weird sentence structure, but I think you get it, hopefully. If not, let me know. Seems okay to me. All right. So what can we use the standardized values for? Well, if we can kind of standardize all these values and figure out how many standard deviations everything is from the mean, well, we can use that. In fact, it's called the empirical rule, or if you've taken stats, you've probably used the 68, 95, 99.7 rule, maybe. At some point, the empirical rule is just the 68, 95, 99.7 rule. I guess they're percentages. But here we're fancy, so we're going to call it the empirical rule. Now, the empirical rule says that roughly, and it sounds silly to have such an exact percentage for a rough approximation, but it works. Roughly 68% of our data is within 1 standard deviation of the mean, right? So if you go down 1 standard deviation and up 1 standard deviation from the mean, you've captured the central 68% of the data. That's a lot of data, right? If you move out 2 standard deviations from the mean, then you've covered the central 95% of the data. Whereas if you move out 3 standard deviations from the mean, then here they say almost all of the data, in fact, should be 99.7% of the data. But I think we can all agree that that is almost all of it, right? Sold. Almost all is 99.7%. If you want to get, right? pretty close to all of it. I just don't like them being that vague about it. Right, so any measure or any value, any observation that's more than 3 standard deviations from the mean should definitely be flagged, right? What's this guy doing here? Because we're expecting, and yeah, there is 0.3% of the data that could happen somewhere else, but it's unlikely, right? So they're worth looking into. In fact, I would argue that most of the time I get suspicious if I find something that's more than 2 standard deviations away, right? So a Z-score more than 2 tells me that, oh, there's something weird's going on here, right? Maybe look into this data point. Maybe it was recorded incorrectly, right? There are all these different options for what happened. You should put that in the group chat, because that is funny. I guess 99.7% is a familiar percentage. It didn't ring a bell for me, but anyways. That's what I was reading here.
Are we going to be tested on this? 99.7%? Is that a...
Oh no, that's why Tara's laughing so hard. I guess it's like the effectiveness of a condom. 99.7%. It's funny.
Fine.
But don't take my word for it. So anyways, almost all. Close but no cigar. All right.
I would ask you how many kids you have. That's, you know, maybe we should move on from this.
For the record, I have no kids.
I guess it's effective.
So visually, right, what we're talking about is not that. What we're talking about is the normal distribution, which I guess hilariously, if you're creative. Anyways, right, and so what's going to happen is that the mean is in the center here. This example derailed completely, but I'm okay with it. So what's going to happen just kind of visually is that here we've got the mean. It is the population mean, but often we'll center it on the sample mean because they should be similar, right? But here I'm just going to call it the mean. And then if I move out 1, 2, 3 standard deviations on either side, right? So 1, 2, 3, kind of lopsided here. What it's saying is that, how can I draw this? What it's saying is that between here and here, so 1 standard deviation, so mu minus sigma and mu plus sigma, we have 68% of the data. That's a good chunk, right? So we're expecting about 68% of our data points to have a Z-score of between -1 and 1, right? Try a different color here. Mu minus 2 sigma, it should be, right? What am I doing? Mu minus 2 sigma is just saying go down 2 standard deviations and then go mu plus 2 sigma up 2 standard deviations. And between here and here, it gets, I've taught this for a lot of years now, and I still don't have a beautiful way of drawing this without it all overlapping each other. But here we've got roughly 95% of our data, right? And then once we get out into the tails, then we're here at maybe mu minus 3 sigma and mu plus 3 sigma. Then we've covered the central 99.7%. I can talk about this distribution for a long time, but what's interesting is that these tails never actually close. They keep going to negative infinity and positive infinity, but the total area that's left over once you pass plus minus 3 standard deviations away from the mean is 0.3%, split evenly amongst the tails, right? That's 0.15% in each tail. Very, very low probability because the area under the curve is going to later translate into a probability. And so rephrasing this, right? The probability of an observation being within 3 standard deviations from the mean on either side is 99.7% or 0.997. Right. So we'll kind of come back to that as we need it, but it's good to remember that the total area under the curve is the probability, right, of something happening. Trying not to say too much about it because we should move on, but yeah, kind of a fun distribution. So in terms of identifying outliers, we are going to introduce 2 methods. So the first one is to look at the Z-scores or those standardized values, right? Any Z-scores that are beyond 3, that's going to set off a trigger, right? Because it's so unlikely that you're going to have that. It's possible, but it's not likely, right? And so they're worth looking into. So we will consider 2 methods of identifying outliers, right? And I'll just kind of clarify what I mean by outliers here are extreme values that deserve a closer look, right? Maybe they were entered incorrectly. Maybe they're there and they're really interesting, right? Or maybe they should be removed because they didn't belong to the population that you thought they did, right? That kind of thing. So I'm going to generalize that and say that deserve attention, right? So extreme values that deserve some attention because they're so needy before being included in our analyses. Okay, so the reasons might be, just to list a few, just to get you kind of going here. Some of those reasons that I mentioned would be data entry error. Right, you could either fix it if you can go back and make sure to see what it should be. It could be just from another population. That's kind of common, right? Oh, that's not actually a value from the population that I was expecting it to be from or wanted it to be from. So then you would have to remove it because you don't want it in your analyses, right? So, or just a truly extreme value, that's an interesting point, right? So maybe I'll leave it at that. Okay, So here they kind of go through some other options. So the first method is to calculate Z scores for each observation in your data set. The other way is kind of the more classic way of identifying outliers, and it's called the 1.5 IQR rule. So we already talked about the interquartile range, and we use that to identify outliers. So let me just write that down. So we'll consider two methods of identifying outliers. The first one is any Z score beyond plus minus 3 is considered an outlier. And I think I mentioned that I'm even suspicious of any Z score beyond 2, right? It kind of, what happened here, right? And it happens, but just something to think about. The other option is the 1.5 IQR rule. What it says is that any value that's beyond 1.5 times the interquartile range from the first and the third quartile, so moving out, I know that's wordy, but I'll show you graphically what I mean, is going to be considered an outlier. Yeah? And so I'll bring in the notes instead, so I'm not saying it twice. The 1.5 IQR rule, the IQR we said was the interquartile range. So I'll make a little note here. Recall that the interquartile range is Q3 minus Q1. All right. So if you have the quartiles, right, then you can find the interquartile range. You can multiply it by 1.5. And then what it says is that if you move down from Q1, right, and I always find it useful to show you the box plot as we go through here. So if you imagine, and I'm going to make this nice and big here. Just kind of ignoring the box plot for a while, even though you've probably seen a box plot at some point. Often they're tilted the other way and we have our scale on the y-axis, but that's okay. This way it makes it nicer to look at because we've got this number line here like we expect to see it, right? And so what a box plot is it draws a box from Q1. So we draw a line at Q1, which would map down to here, right? That's Q1. And the box to Q3. What's this box showing? That's the central 50% of our data, right? Split in half by the median, or potentially not in half, right? But the median is the line in the middle here. And so that's where we show our median measurement. And that's the point that splits our data in half, right? Kind of counterintuitively, at least to me, is that the smaller the distance is, the more data we have in between there, right? Because it took a shorter distance to move from the median to Q3. But that's 25% of our data, right? Whereas from Q1 to the median, it took us a little bit longer. And I'm saying longer in terms of a distance on a number line, right? To cover that same 25%. So we can look at the distribution of a box plot and essentially if there's symmetry, right? So if each quartile is the same distance, then you have a symmetric distribution, right? And so, so a box plot is just drawing a box. You draw your first line at Q1 and then your second line at Q3, maybe draw a median, connect them with a box. That's like kind of the meat and potatoes of your data, right? The middle 50%. The interquartile range is the distance between those two. And so, and then we have what we call the whiskers. Now the whiskers here is going to be how we determine if we have outliers. So the whiskers we find by, the whiskers are drawn. This is also how we find outliers. The whiskers are drawn from the ends of the box to the smallest and largest values inside the limits computed in step 3, which I'll summarize here. The lower limit is going to be Q1. From Q1, we want to move down some distance because we allow some distance without calling them outliers, right? So from Q1, we're going to go minus 1.5 times the interquartile range. And people will usually ask, oh, why is it 1.5? What's the significance of 1.5? Well, it's what people sat down at some point in a room and said, yeah, that's good. Could be 2, could be 3, could be 1.27 if you wanted. And I'm sure you could build a thesis around that. But access denied because we've all decided 1.5 is fine. But there are other measurements. I'm pretty sure it was Tukey, who is a famous statistician, who argued that 1.5 was a good trade-off between not having too many outliers, but also being able to detect outliers if there are any, right? And that's the goal. So the lower limit is going to be down from Q1, right? 1.5 times the interquartile range. And then the upper limit is going to move up from Q3, right? So now it's going to be Q3 plus 1.5 times the interquartile range. I'm going to highlight that those two are different, right? Because it depends on if you're going down a little or up a little. Okay. But then these whiskers, which is kind of a cute name, right? The whiskers go to the data points that are still within the, the whiskers go to the data points that are still within those upper and lower limits, right? And then any data point that's beyond that limit is denoted by typically a little asterisk or a dot. And that's to indicate that this value is considered an outlier. And again, if it's considered an outlier, you should kind of look back and does that data point make sense? Should it be included? Yes or no? No. Don't include it. Usually we're trying to keep as many data points as we can. Although in grad school, I had a lot of friends who did biology, and if they had one they didn't like, they just ditched it. Sometimes just got rid of it. Oh, I don't like that one. Oh, okay. So it depends on, well, if you're collecting the measurements, then I trust that you're able to identify when you've measured something incorrectly and you can remove it. So you're allowed to do that in that case. Okay, good. So those are the two ways that we can identify outliers, right? And then once we've identified them, then we can look into them and kind of suss out what they are. Should they be there? Should they not be there? right? And so a box plot is just a nice way to visualize data, right? And so we can use a box plot to visualize data, or maybe the distribution. Oops. Nope, still no. The distribution of a variable. Right? If there's symmetry around the median, okay, so if there is symmetry, and I'll show you an example. If there is symmetry about the median, right, which is that central line, we have a normal distribution. Typically. So we can compare distributions, and usually this is how we use the box plots, is using side-by-side box plots. And what's nice here is we get to see a couple of different distributions, right? And so now, right, we've got this categorical variable that split our data up into different categories, right? And so this is how we typically end up using a lot of our categorical variables. So here I want to highlight that this, whatever it is, it looks like it's communities, right? So here, these would be our categorical, or a categorical variable with the categories here on the x-axis, right? And then we have the selling price, probably of home prices. I don't remember the example, it doesn't matter. But notice how here's the median, right? So now we know that the central line is the median, and on the lower end, we've got the first quartile, on the upper end, we've got the third quartile, right? And then we've got these whiskers. Considering the symmetry around the median of the Fairview community, it's not symmetric, right? And so here we notice that this is not symmetric. Not symmetric, therefore not a normal distribution. What gets weird, like I said, I'm out of time. Let me just say this one last thing, is that with these shorter distances, it means that we have more data, which means that we have more data on the lower end, which means that this would translate to, and just kind of stay with me for just a little bit longer, something like this, right? Skewed to the right, because we've covered the first 50% of our data in a short amount of time, because we have that blob there. And then it's going to take us longer to cover the remaining 50% of our data, right? So if you have symmetry here, I would call this relatively symmetric. So it's relatively a normal distribution. Here's a skewed distribution, skewed in the positive direction, because if we lay this down and make it a number line like this, right? And so it takes definitely some concentration to look at these, right? But the key thing to remember is that if there's symmetry, now this doesn't look like it's a huge data set, but it's beautiful and symmetric, right? So if there's symmetry, then you can say that you have a normal distribution, right? But also, I know I'm out of time, but you can also compare the medians and the values and everything by just looking at the side-by-side box plots. Done. If you have any questions, let me know. Otherwise, we'll keep going on Wednesday. We'll stop this recording.